In this section, we will look at sum and difference identities for the tangent function. Now that we know the sum and difference identities for the sine and cosine functions, we can derive the sum and difference identities for the tangent using the quotient identity that says that the tangent of an angle is equal to the sine of that angle over the cosine of that angle. So, using the sum identities for sine and cosine, we can say that the tangent of some angle alpha plus some other angle beta is simply equal to, in the numerator, the sine of the quantity alpha plus beta over the cosine of alpha plus beta. So we are going to be using those identities. The sine of alpha plus beta is listed here for us, that identity, and the cosine of alpha plus beta is also listed for us. We've seen these before. So I'm just going to go ahead and substitute those in, and it's going to look like this. All right, so let me just highlight for you here. In the numerator, I have sine of alpha times cosine of beta plus cosine of alpha times sine of beta. That comes directly from the identity that we've learned previously. In the numerator, the denominator, I have cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And that comes directly from the sum identity for cosine that we've previously learned. All right, now, sometimes in proofs, some weird things happen, and this may be one of those cases, but I think you'll see why I'm doing this in a minute. I'm going to take the numerator and the denominator, and I'm going to divide both of those by the cosine of alpha times the cosine of beta. All right, so in red, we see that we are dividing those into both the numerator and the denominator. Now, why would I want to do that? Well, let me show you what happens. Here's how I can rewrite this, all right? I can take that cosine of alpha times cosine of beta. I can distribute that. That belongs to each part of the numerator. So what you see, let me highlight this for you. And I'll do it in maybe a different color. So sine of alpha times cosine of beta divided by this cosine of alpha, cosine of beta, that's what is right here in my very first term. Then I'm going to take plus, I'm going to take cosine of alpha times sine of beta, and I'm going to divide that by the cosine of alpha times the cosine of beta. I'll do the same exact thing for the denominator. So I'm going to take the cosine of alpha times the cosine of beta, and I'm going to distribute that to each one of those terms. And when I do that, that's where, let's see, I've got cosine of alpha times cosine of beta. I'm going to divide that by that cosine of alpha, cosine of beta. All right, so here is. And so that is what I get. All right, so like, why the heck am I doing that? Well, let me show you what's going to happen here. It's going to be nice. In this very first term, notice that the cosine of betas cancel out, and I'm left with the sine of alpha over the cosine of alpha. And we know that sine over cosine is simply tangent. So that reduces nicely. Okay. Plus, let's take a look at the second term in the numerator. Does anything cancel out? Looks like the cosine of alphas cancel out. So now I'm left with the sine of beta over the cosine of beta, which is the tangent of beta. All right, so we've got that. That looks a lot better. Now let's go to the first term in the denominator. Not only do the cosine of alphas cancel out, but the cosine of betas cancel out as well. So I'm left with 1, okay? Minus, let's look at the second term in the denominator. Does anything cancel out? Let's see, does anything cancel out? sine of alpha, cosine of alpha, sine of beta, cosine of beta. Looks like nothing cancels out, but what I do have is the sine of alpha over the cosine of alpha, which is the tangent, the tangent of alpha, and then the sine of beta over the cosine of beta, which is the tangent of beta. And let me just show you what that formula, that identity actually is. And I think this will look familiar to you. Let's verify that what I just came up with for the tangent of alpha plus beta really is the same as this identity that's listed. So the tangent of the quantity alpha plus beta is simply equal to, in the numerator, the tangent of alpha plus the tangent of beta all over 1 minus the tangent of alpha times the tangent of beta. Now, we're not going to go through that same process for the difference, tangent of alpha minus beta, but we could go through an exact same process to come up with this identity, which is identical to what we just came up with the exception of the signs that are here. All right, so those are those two new identities that we can work with. Now let's try an example where we're being asked to find the sum and difference of not only the sine and cosine, but now also the tangent. All right, so let's first take a look at what we're given. We are given that the sine of an angle alpha is equal to 5 over 13, where alpha is between negative 3 pi over 2 and negative pi. You might need to draw yourself a circle to vision where alpha is. And once you've done that, I think that you'll see that alpha is in quadrant 2. So I'm just going to make a note of that for myself, right? That's going to be in quadrant 2. And let me see if I'll just help you a little bit. So negative pi is starting on the positive x-axis, and it's going clockwise to negative pi. Negative 3 pi over 2 is all the way over to actually where pi over 2 is. So that is the space in that second quadrant. That's what we're talking about. All right, the second piece of information that's given is that the tangent of beta is equal to negative square root of 3, where beta is between pi over 2 and pi. So this one's also going to be in the second quadrant. Okay, and so part A says to find the sine of alpha plus beta. So let's make sure that we have our identities near us. And what I notice in all of these is that I'm going to have to know something about not just the sine of alpha, but probably the cosine of alpha. And not only the tangent of beta, but also something about the sine of beta and the cosine of beta. And I guess I'm probably also going to have to know something about the tangent of alpha. So before I start this process, I think I'm just going to go through and do all of those pieces. So I'll start with the sine of alpha. I see that that's equal to 5 over 13. And what I know is that cosine squared alpha plus sine squared alpha is equal to 1. So I'm going to substitute in the place of the sine of alpha. I'm going to put in that 5 over 13. It's not alpha, but it's the sine of alpha. And I'm going to square it and set it equal to 1. Solving, I get that cosine squared alpha is equal to 1 minus, let's see, 5 times 5 is 25, and 13 times 13 is 169. 1 minus 169 is the same thing as 169 over 169 minus 25 over 169. That gets me 144 over 169. Go ahead and verify that yourself. That's what cosine squared alpha equals. So now I'm going to square root each side. I'm going to square root each side, and I get plus or minus 12 over 13. Now, is it a plus or is it a minus? Well, this is where paying attention to the quadrant comes in handy. In the second quadrant, the cosine is negative. So I'm going to call this negative 12 over 13. And I think I'm going to start highlighting here so I can keep track of things. I was given the sine of alpha. Now I know the cosine of alpha, don't I? Let's go ahead and just find out the tangent of alpha while we're at it. Tangent of alpha is sine over cosine. So I'm going to take 5 over 13, which is my sine, and I'm going to divide it by the cosine. Now, cosine is negative 12 over 13, so I'm going to go ahead and just multiply by the reciprocal. I can see that I'm going to need to do that anyway. And the 13s cancel out, and I find out that the tangent of alpha is equal to, it looks like negative 5 over 12. All right, so let's highlight that as well. So we know a lot of things about alpha, don't we? Okay, let's move on to beta now. What we know about beta is that the tangent of beta is equal to negative square root of 3. Now, this is a little bit tricky because I have to find out sine and cosine. So let's remind ourselves that, I may run out of room here. Let's see. Remind ourselves that the tangent of an angle is equal to some y value over some x value. Now, in this case, because I'm in quadrant 2, I know that the x value will be negative and the y value will be positive. So if this equals negative square root of 3, I could say that that's equal to the square root of 3 over negative 1. And that's what my x and my y value are. Now, how does that help me? Well, what I know is that the sine of an angle is equal to y over r, isn't it? And I also know that the cosine of an angle is equal to x over r. So I know my y and I know my x. If I can find r, then I think I'm in business. What is r? Well, let's just do this off to the side here. We're going to say that x squared plus y squared is equal to r squared. Okay, so that's 1 plus 3, which is 4. I think we can say that r is equal to 2. So my sine of beta is equal to my y value of the square root of 3 over my r value of 2. And the cosine of beta is equal to my x value of negative 1, also over 2. Okay, so let's highlight those. Okay, so we know a lot of information. Now we just got to put it all together. So for part A, let's see if I can get this in there. So the sine of alpha plus beta is going to equal, identify the correct identity. It's going to be equal to the sine of alpha, and the sine of alpha is given to us as 5 over 13. I'm going to multiply that by the cosine of beta, so times negative 1/2. I'm going to add that to the cosine of alpha. Cosine of alpha is negative 12 over 13. And I'm going to multiply that by the sine of beta, which is the square root of 3 over 2. All right, that looks pretty good. Now notice in the denominator, both denominators are going to be 13 times 2, which is 26. So I'm going to call that, let's just say, looks like I'm going to have negative 5. Looks like I'm going to have plus negative 12 times the square root of 3 all over that 26. And that's a great answer. I will tell you that with the double negatives here, one thing that I could do, I don't have to do, but I could pull a negative out and then just have 5 plus 12 root 3 on the top. That negative that's pulled out to the side does not belong to both the numerator and the denominator. If I wanted to multiply it back through, I would either multiply it through to the numerator terms or the denominator. So it would be equal. All right, so that's what the sine of alpha plus beta is. I'm going to do part B in a different color. Part B says to find, the cosine of alpha plus beta. So what does that equal? Cosine of alpha plus beta is going to equal the cosine of alpha. What is the cosine of alpha? It is negative 12 over 13. And I'm going to multiply that by the cosine of beta, which is negative 1/2, minus the sine of alpha, that was given to us as 5 over 13, times the sine of beta, which is square root of 3 over 2. Notice that it looks like my denominator is that 26 again, isn't it? So I'm going to put 26 in my denominator, and up in my numerator I get negative 12 times negative 1, which is simply 12, and then 5 times the square root of 3, so minus 5 times the square root of 3. Okay, so there's those two answers. Let's see if I can squeeze one more in, and I'll do this one in red. All right, part C says, what is the sine of alpha minus beta? What does that equal? The sine of alpha minus beta has been given to us as the sine of alpha. Sine of alpha is 5 over 13 times the cosine of beta times negative 1/2 minus the cosine of alpha. Cosine of alpha is negative 12 over 13 times the sine of beta, which is square root of 3 over 2. What does that equal? Again, we've got that 26 down in the denominator, and so I'm going to put that all over. Looks like I'm going to have negative 5 plus 12 times the square root of 3. Now, another way of writing that, a lot of times you'll see books that won't have your leading term with a negative on that, just because it can be confused as subtracting something. So what I could do is rewrite this, if I wanted to, as 12 square root of 3 minus 5 over 26. It would mean exactly the same thing. Now, I'm running out of room, so I might be going to the next slide, but let me just highlight what we have so far. For part A, which was the sine of alpha plus beta, we came up with negative in my numerator, 5 plus 12 root 3 all over 26. For part B, for the cosine, we came up that was equal to, in the numerator, 12 minus 5 root 3 over 26. And for part C, I came up that is equal to, in the numerator, 12 root 3 minus 5 all over 26. Let's go to the next slide and do the tangent. Now let's take everything that we just learned to find part D, which is the tangent of alpha minus beta. So let me write that out. The tangent of alpha minus beta is equal to, it looks like it's going to be equal to the tangent of alpha, and the tangent of alpha is negative 5 over 12 minus the tangent of beta. Tangent of beta was given to us, so we're minusing a negative, which is the same as adding, so square root of 3, over, the whole thing over, 1 plus the tangent of alpha, which we said was negative 5 over 12, times the tangent of beta, which is negative square root of 3. So negative square root of 3. All right, let me simplify that maybe just a little bit, and I will call this negative 5 over 12 plus the square root of 3 all over 1 plus 5 times the square root of 3 over 12. Now, that's basically what it is, but we now want to make it look a little bit better. And there's lots of ways that you can do this, but when I have fractions within fractions, what I like to do is clear those fractions. And in this case, I'm going to multiply the numerator by 12. Now, when I say 12, I mean 12 over 1, right? That's what 12 is. If I do that in the numerator, I'm going to have to do that in the denominator as well. So when I multiply 12 by each of the terms in the numerator, I get, let's see, it looks like I get -5 plus 12 times the square root of 3. That looks a lot better. In the denominator, what happens in the denominator? When I multiply 12 times 1 and then 12 times this second term, I get 12 plus, now the 12's canceled out, numerator, denominator, so I'm left with 5 times the square root of 3. And that looks great. Sometimes people will have you stop there, but there is a radical in the denominator. So what oftentimes instructors will ask you to do, or math books will ask you to do, is rationalize that denominator. And the way that we can rationalize a denominator that is a binomial is by multiplying it by the conjugate. Okay, I'm going to move to the next space here because this is going to take a little bit of room. So I'm going to take -5 plus 12 root 3, and I'm going to write down the 12 plus 5 root 3. The conjugate of that denominator is the exact same thing, only instead of a plus, there's going to be a minus there. And I'm going to do that on the bottom, and I'm also going to do that on the top. And I'm going to have to FOIL this out. So what does that equal? Well, let's see. I'm going to get -5 times 12, which is -60. I'm going to get -5 times -5 root 3, which is plus 25 root 3. Let's see. I'm going to get 12 root 3 times 12, which is plus 144 root 3. And then 12 root 3 times minus 5 root 3. Well, 12 times 5 is 60, and square root of 3 times square root of 3 is 3, so I'm going to get minus 180. Okay. In the denominator, some nice things should happen now. 12 times 12 is 144, and then the reason we multiplied by that conjugate is because 12 times minus 5 root 3 and 5 root 3 times positive 12, those are going to cancel out, aren't they? And so I'm left with simply 5 root 3 times 5 root 3. One of those was a minus. So 5 times 5 is 25. Root 3 times root 3 is 3. So I get minus 75. All right. So the last step now is just to simplify. Up in the numerator, it looks like I've got some like terms. I've got the -60 and the -180. -60 and -180 is -240. And then I also have the roots, don't I? And they both are root 3, so that's good. I can add those. 25 plus 144 is 169 root 3. And in the denominator, 144 minus 75 is 69. Now there are no common factors here, and so there's nothing left to reduce, and we are done. Now on the last slide, I did show you this YouTube link. If you want some more examples of rationalizing denominators, you might check this out because it can be a little bit confusing and it may be a while since you've done this.